In this lecture, we will be covering the topic of higher order derivatives. So if we're given a function, f, and it has a derivative, f prime, f is a function. If it has a derivative, its derivative is also a function. If that function f prime is also differentiable, then we can take its derivative. And that derivative we call the second derivative of f. Simply the derivative of f prime. And we denote it by f double prime. Here we have some notation. The second derivative of f is the derivative with respect to x of f prime of x, or the derivative with respect to x of the derivative with respect to x of f of x, which we will often write shorthand as the derivative with respect to x with this superscript 2, meaning we're doing it twice. The nice thing about second derivatives is that once you're used to calculating derivatives, calculating second derivatives is quite natural. So for this example, we know if f of x is x cubed, our power rule tells us the derivative is 3x squared. To take the second derivative, we take this f prime of x and differentiate it. And the rules are all the same. So we use power rule again here to get 6x for the second derivative. Now, there's no reason why we have to stop at a second derivative. We can go one step further and take a third derivative. So if our function f has a second derivative, and that second derivative is also differentiable, we can take its derivative, which is going to be the third derivative of f, which we would denote by f triple prime. So to continue with our previous example, we can take the derivative of f double prime, and we know the derivative of 6x with respect to x is 6. And you can see where this is going. We could do a fourth derivative. And there's usually two ways people will write it, either Roman numerals or the number in parentheses. Of course, the derivative of 6 with respect to x is just 0. And you could keep going. You can go the fifth derivative. The derivative of 0 with respect to x is 0. So these will all be 0 afterwards in this case. And this leads us to the general definition of the nth derivative. So this should be our nth order derivative. So our nth derivative, we just write, like we had mentioned there, the superscript of n in parentheses, or with a Roman numeral. To look at an interesting example, let's get away from polynomials for a minute. Let's think about this sine function. Let's calculate the first derivative. Now remember, the derivative of sine of x with respect to x is cosine of x. So there's our first derivative. Our second derivative, the derivative of the first derivative, the derivative of cosine of x with respect to x is minus sine of x. For our third derivative, the derivative of sine of x is cosine of x, but we keep that minus sign out front, so we get minus cosine of x. Let's take the derivative of that. So the fourth derivative, well, the derivative of cosine of x is sine of x, negative sine of x. And we have a negative sign out front still, so minus minus sine of x, or sine of x. So that gives us the first four derivatives of sine of x. But now let's note something. Look at this set of higher order derivatives and think about the pattern. And what you want to note is that this fourth derivative matched the original function. How about the fifth derivative? Well, we're differentiating sine of x. We won't get any different result than when we differentiated sine of x here. So we'll get cosine of x. And note that first and the fifth derivative match. And this continues. The g sixth derivative of g will be minus sine of x. And we see that this matches the second derivative. So we see that the pattern repeats in this case. So this is something you'll actually revisit again in detail later in calculus when you start to explore the topic of Taylor series. So this is a very famous pattern. But yeah, we see that this pattern repeats in these blocks of 4. Okay. Let's talk some more notation. When we introduce differential notation, we have another way of representing these derivatives. We're already used to writing dy dx for f prime of x when we have y equals f of x. The notation that we use for a second derivative is this, and you would read it d squared y dx squared. This is shorthand for the derivative with respect to x of dy dx. Maybe easier to think of this way. The derivative of the function dy dx with respect to x. And then you have the same type of notation for these higher order derivatives. So we have, in this case, for the third derivative, this would be the derivative with respect to x of the second derivative, which is the derivative with respect to x of the derivative with respect to x of dy dx. So again, an alternative notation for derivatives. This actually becomes quite important when you move into the field of integral calculus. In particular, when you start doing calculus, multivariable integral calculus. Let's do some more examples. Y equals e to the x. Well, this one, remember, e to the x, its derivative with respect to x is itself. So if we take a derivative again, nothing's going to change here. Second derivative with respect to x is e to the x. Third derivative, fourth derivative. In general, the nth derivative of e to the x with respect to x is e to the x. How about e to the minus x? Well, dy dx, we know with chain rule, we have a minus e to the minus x. So the derivative of the outer function, leaving the inner function alone, that gives us e to the minus x, times the derivative of the inner function. The inner function is minus x, whose derivative is minus 1. But if you continue this, the derivative of minus e to the minus x, the procedure is the same as when we differentiated e to the minus x, but this minus sign hangs out front. So you're going to get a minus e to the minus x, or e to the minus x. And thinking of patterns, you see the first derivative, the original function and the second derivative are the same. If we go again and take the third order derivative, d cubed x, d cubed y dx cubed, we differentiate e to the minus x. We'll get the same answer as when we did it here. And so we get minus e to the minus x. And again, note, this third derivative matched the first derivative. So the result here is that our higher order derivatives, if they're odd order, we get a minus e to the minus x. So we can say the derivative, well, how do you write an odd integer? 2n plus 1. That's going to be minus e to the minus x. And so think of n as being one of the counting numbers in these two general statements. Or we should actually say a little bit more specifically, because we need to include 0. N is in the non-negative integers. So 0, 1, 2, 3, so on and so forth. So for n in that set, so if n is 0, we would have the first derivative. If n is 1, we have 2 times 1 is 2, plus 1 is 3. We would have the third derivative. If n is 2, we have the fifth derivative. If we want to do even order derivatives, we just do 2n. And in that case, we get, as we saw here, e to the minus x. Another example, f of x is natural log of x. We learned in an earlier lecture that the derivative of natural log of x with respect to x is 1 over x. Well, it'll be easier for us if we write it as x to the minus 1. So to take the derivative of that f prime of x, we would need power rule. So minus 1, x to the minus 2, or minus 1 over x squared. For our third derivative, power rule again. Bring that minus 2 out front, reduce the power by 1. So in this case, we would get a positive 2 over x cubed. For the fourth derivative, power rule on the second derivative. The minus 3 comes out front. X to the minus 4. Or here we have minus, minus, minus. So that's a minus 6 over x to the fourth. Why don't we identify the pattern? Fifth derivative of x. Again, bring the minus 4 out front. Minus 4, minus 3, minus 2, minus 1, x to the minus 5. Now, one thing to note here, we've been multiplying these out, but 4 times 3 times 2 times 1, that's called 4 factorial. We have x to the minus 5. And we had 4 copies of minus 1. So we had minus 1 to the fourth power. If we kind of backtrack and identify the pattern for the fourth derivative above, we had 3 copies of minus 1 and a 3 factorial. Times x to the minus 4. Above here, we had 2 copies of minus 1 and 2 factorial. Up here, we had one copy of minus 1. And 1 factorial is defined as 1. And then in this case, we had 0 copies of minus 1. We could say 0 factorial. Remember, by definition, 0 factorial is 1. And we actually can identify the pattern here from this. We can say this tells us that the nth derivative of f, and see if you can just generalize what we did. So here, n was 5, and we had a 4 factorial. Well, if n is 5, 4 is n minus 1. How many copies of negative 1 did we have? Well, again, n was 5. We had 4 copies of minus 1. So we get minus 1 to the n minus 1. And then x here to the minus 5, which was n. We have x to the minus n. So we could write this as minus 1 to the n minus 1 times n minus 1 factorial. Bringing the x to the minus n down bottom, we get x to the n. This is another very famous derivative, higher order derivative pattern, again, which you will revisit in detail when you learn about Taylor series later in calculus. One last example will illustrate a case where higher derivatives can start to get kind of messy. In particular, chain rule and product rule can cause you trouble. I wouldn't say trouble, maybe I should say complicated higher order derivatives. So in this case, g prime of x, we need our product rule. First, x squared times the derivative of the second, e to the x, plus the second, e to the x, times the derivative of the first, 2x. This will be nicer if we factor. E to the x times x squared plus 2x. But you can see now this first derivative is more complicated than the original function. So when we start going for higher derivatives, here, product rule again. First, e to the x times the derivative of the second, 2x plus 2. Plus the second, x squared plus 2x, times the derivative of the first, e to the x. Again, let's factor. E to the x is common. We have an x squared plus 2x plus 2x. So x squared plus 4x plus 2. And you can see how things are getting even more involved. Let's do another one. Third derivative of x. Again, product rule on the second derivative. First times the derivative of the second, 2x plus 4. Plus the second, x squared plus 4x plus 2 times the derivative of the first, which is e to the x. Factoring. We have 2x plus 4x is 6x, and then 4 plus 2 is 6. So we've leveled off in terms of how complicated things get. We're not going to get worse than this second order polynomial here. But it is an example that when you start doing higher derivatives, things can get complicated. Let's look at an example that would get really messy really quickly. So our seventh example. Suppose we have f of x equals cosine of x squared. First derivative, we need chain rule. Derivative of the outer function minus sine, leave the inner function alone, times the derivative of the inner function. Fairly straightforward chain rule calculation. But now if we start doing higher order derivatives, note that we have to use product rule and chain rule. So product rule first, minus sine of x squared, times the derivative of the second, 2, plus the second, 2x, times the derivative of the first. Chain rule, derivative of the outer function. Derivative of sine is cosine. We still have a minus sign out front. So minus cosine of x squared times the derivative of that inner function, which will be 2x. Cleaning things up, we get minus 2 sine of x squared minus, we have 2x times 2x, so minus 4x squared times cosine of x squared. And now, hopefully, we can see this is quite a bit more complicated than the first. And so if we continue with higher order derivatives, it gets a little bit messy. Let's do one more to see. So we have the third derivative. So for this first term, we have the minus 2 sticks around. The derivative of sine is cosine. Leave the inner alone, times the derivative of the inside. Now for this second term, we will have minus, let's put it all in one big block. First, 4x squared times the derivative of the second. So the derivative of the outer function here, which is cosine of x squared. The derivative of that outer function, we have minus sine, leave the inner function alone, x squared, times the derivative of the inner function, 2x. So this was our first part of the product rule. Again, first, 4x squared, times the derivative of the second, minus sine, leave the inside alone, times the derivative of the inside. Second product rule term, plus the second, cosine of x squared, times the derivative of the first. Power rule, 2 times 4 is 8, x to the first power. Cleaning things up a bit, we have 2 times 2 here, so we have a minus 4 cosine, I missed an x, minus 4x cosine of x squared. For the first term in here, we have a minus minus, so plus. We have 4x squared times 2x. That's 8x cubed times sine of x squared plus 8x times cosine of x squared. And this illustrates we had a pretty simple original function. And when we started doing higher order derivatives, we got pretty complicated pretty quickly. It tends to be chain rule and product rule that makes these things get ugly like this. So hopefully this illustrates how second, third, fourth, nth order derivatives work. The nice thing about this is there's no new rules to learn. All your differentiation rules are exactly the same. All this is saying when you take a derivative, you get a function. If you can differentiate it, you use the same rules that we've already learned so far for taking derivatives.